So recall that when we brominate an olefin, we attack the bromine sigma star at the same time as we're forming a new carbon-bromine sigma bond. Lone pairs on the bromine are attacking the other carbon so that we never get a carbocationic intermediate. Instead, we get this bridged bromonium ion that gets attacked from the backside in SN2 fashion. And then you get these two products, which we called anti-diastereomers. We said this is an example of a reaction that's stereoselective for the anti-diastereomers, having the Br on opposite sides of the original alkene. Now, there's been some confusion about how do you tell whether a particular diastereomer is syn versus anti. And the answer is you have to know what the starting material was. So as an example, let me show you this product. You've got bromines on adjacent carbons, so this looks like something you might have made via a bromination reaction. But if you look at it from this perspective, it looks like the BRs were added on the same side of an alkene. But what if we rotated around a carbon-carbon bond by 180 degrees? We'll keep carbon 2 in the same place, but now we'll have Br, instead of pointing out at us, going back into the page. Now it looks like possibly an anti-product, right? And in fact, we could have gotten this product from bromination of the trans or E alkene. So you can't look at a product and say whether it's syn or anti. In order to know that, you have to know what the starting material was. Because when we say syn versus anti, we're talking relative to the carbons of the original double bond. So if we draw the carbons in the same orientation and shape they were with the original double bond, then when we see the BRs on opposite sides, one pointing up towards us, one pointing down away from us, then we can say, yes, this is the anti-product of this starting material. But if we changed the alkene configuration and did the same reaction, we would get this product, which does look like an anti-product. But the only reason it looks like an anti-product is that I've just continued to draw the atoms of the double bond in the same orientation. I should point out that the molecule I've drawn is chiral, and we would get the other enantiomer as well. But I will also point out that you could draw this molecule by rotating 180 degrees. You could draw this molecule in a different orientation that might make it look like a syn product. So what I'm saying is this diastereomer syn or anti? Meaningless question unless you talk about the starting material itself, all right? Relative to the Z alkene, this product is an anti-product. Okay. Questions on that? Stereochemical issues? No? All right. So one thing that can help keep all of these reactions straight and can help you build up synthetic skills, the ability to design syntheses of larger molecules, is to recognize structural patterns. Having two bromines on adjacent carbons, we call that sometimes a vicinal dibromide or dihalide. Vicinal means neighboring. And when you see a vicinal dihalide, you should be thinking, oh, I could have got that from a bromination reaction. Yeah?
Sorry, so is that bottom one anti as well, or is the bottom one the same?
The bottom one is the same. I've just rotated around carbon-carbon bonds. And that's the trick, is that once the double bond is gone, you can rotate around bonds to all sorts of levels of confusion, and it doesn't change anything. These two are the same thing, and together these are anti-products of the cis alkene. All right. Okay, other questions? Vicinal means neighboring, yeah. Another place where we've seen a similar pattern, just to review, has been epoxide opening. We haven't learned how to make epoxides yet, but there are similar stereochemical issues associated with epoxide opening. Epoxide opening, say, with hydroxide under water conditions, would give you a product that looks very similar to the vicinal dibromide, only the players are OH instead of Br. But a similar sort of pattern, 1,2 vicinal diol, you could have gotten by opening up of an epoxide. And notice the similarities. With bromination, we go through bridged bromonium ion intermediate. The epoxide already has that three-membered ring structure. So being able to recognize these types of structural patterns can be useful. I could show you the products that we would get from the trans epoxide opening, and they would be similar to the products we got from bromination of the trans alkene. So be able to follow through those stereochemical issues. As I said, I haven't told you how to make epoxides yet, and we'll talk about it, but it's key to be able to take a starting material with a particular stereochemistry and follow that stereochemistry through into the product. All right. So whether it's syn or anti is determined by the mechanism of the reaction, but syn or anti is always described relative to the starting material, the way the double bond was in the original starting material. Okay, so the next reaction on our list has a different name, but it's not useful at all to think of it as a different reaction. It's the same as bromination, only we're going to use a different nucleophile in the second step. Your text calls this halohydrin formation, as though we needed some other name to remember or memorize, and that's not particularly useful. We'll start with the same cyclohexene starting material, and we're going to do the reaction, but instead of doing the reaction with bromine in a solvent that can't be a nucleophile, let's do the reaction in a solvent that can. Let's use water as the solvent. This reaction also works for alcohols. So as before, you form a bridged bromonium ion intermediate. The mechanism for forming that is written above. But in the second step, you've got this competition between Br- and water. All right, so Br2 is the reagent, water is the solvent. Usually you would only put in 1 mole of Br2 for every mole of alkene. But usually solvent is present in vast excess. You can use the density of water and its molecular weight to figure out what the molarity of pure water is, and it's like 55 molar. So in terms of concentration, we have way more water than Br minus at this stage. So water, just by stoichiometry alone, outcompetes Br minus in the second step of this reaction. Water opens up the bromonium ion. I will point out that atoms A and B are identical here, so water could have attacked either one. If it attacks B, we'll get this product. If it attacks A, we would get the enantiomer. And then we need to remove the proton from the protonated oxygen, the positively charged oxygen. Again, doing this is reasonable just based on pKa's and by the fact that we have a lot of water present. And so, yes, the products of this reaction have Br on one carbon and OH on the other, and then, of course, this enantiomer. Okay? So it's exactly the same as bromination, only you intercept the bromonium ion with water. Yeah?
Why is the water negatively charged?
Why is the water negatively charged? Because I'm crazy. Sorry about that. Or rather, I had a momentary lapse in judgment. So, Hannah, I'm sorry, you said something about enantiomers, but I missed it.
Yeah. When you drew enantiomers, you actually just drew the same molecule.
Oh, yes, thank you.
Future me is going to be super.
Yeah, me too. Sorry about that. I should have changed the stereochemistry. I guess if I wanted to, I could have drawn it like that. Is that better? Ish. Okay, thank you. Sorry for that. My apologies. Okay. Other questions? Yeah.
So in an actual reaction, you have the OH group attached in some of them, and then you have a bromine attached in others. Does that make sense? Just because you have a lot more water, you'll have a lot more molecules that look like that, but bromine, would that also reaction?
So, yeah, the question is, do you ever get, from this reaction, do you ever get some of the vicinal dibromide where Br minus comes in and does the attacking? It sounds reasonable to me. We're just gonna pretend like this reaction works perfectly. Usually, for organic reagents in water, usually the concentration is submolar, so we're talking in the 0.001 or perhaps just 0.1 molar concentrations. So you're talking about at least 500 times as much water as Br minus, and so that would make it difficult to see any of the dibromide under these conditions. So I think you're right to worry about it, and if you go in the lab and do this and isolate some dibromide, then you'll know exactly where it comes from, but we're going to pretend like this reaction works fine. Yeah?
I figured out, I was just going to ask, like, with the oxide ring, if it's always going to keep up or if you try it down as well.
The epoxide ring up here? Oh, the bromonium ion? Yeah, you could write it down, and in fact, this bromonium ion is achiral and meso, so it would be the same from above or below. I saw another hand. Did I? No? Go ahead, Hiram.
Yeah. Okay. Isn't the hydroxide a good leaving group? And was the bromine not attacked from?
Isn't the OH is not a good leaving group, but at this stage, whoops, I don't know, I'm scribbling stuff out. And at this stage, OH water is a good leaving group, and I suppose you could have the bromine attack. That would just be going backwards, and don't know what the relative rates of the forward and reverse reaction are, so I can't really tell you how reasonable that is. It sounds okay.
I meant to ask if the second bromine would attack there.
Oh, would a second bromine attack there? No, because again, it would be hard for that second bromine to find this. I think it's worth worrying about, but look at what does the deprotonating. And again, there's way more of that. There's way more of water than there is Br minus, which means that going to the neutral product is going to be a lot faster than this hanging around for another Br to come in and attack. All right, and
Can I ask you a question really quick?
sure.
I was just wondering, in the last step of the process that we've shown, why does the lone pair attack the proton on the H2O? It just seems to me that would create a really unstable
Okay.
conjugate acid.
Okay.
I'm just kind of surprised. Like H3O plus, I feel like that would break down a lot,
Okay.
really easily.
All right. Yeah. Let's talk about that. So the question is, why does water do the deprotonating here? And so basically, this is an acid-base question, and I haven't drawn the conjugate acid on either side of the equation. So to determine how reasonable this is, we simply need to remember our Chapter 2 pKa skills. A protonated alcohol has a pKa of -2, and H3O plus also has a pKa of -2. What that means is we would expect this, all things being equal, we would expect this equilibrium constant to be close to 1. But we have way more water in solution than we have protonated alcohol, and that's going to push the reaction towards completion. Now, you're right, and one thing you notice is that this reaction produces H3O plus and Br minus. So yeah, it's going to be an acidic aqueous solution, and probably to work up this reaction, you would need to neutralize the solution. But in terms of pKa's alone, this is reasonable. Another question from the chat is, why doesn't Br minus do the deprotonating? Your text may show that in the mechanism, but what I've shown you here is way more reasonable by virtue of the fact that there's more water present than Br minus, and also by virtue of the fact that HBr is a much more acidic compound than H3O plus. That being said, I wouldn't mark it wrong if you showed Br minus doing the deprotonating. Yeah.
Could we also assume that the partial positives in the water would kind of surround the bromine and hide it from being able to attack?
Sure. So the question is, wouldn't bromine become a little less nucleophilic in water because it's going to be in a cage of water molecules that are hydrogen bonding with it? That sounds like a decent explanation as to why it wouldn't be a good base under these conditions and why it wouldn't come in and attack attack this leaving group. Okay. So the term halohydrin refers to a molecule that has oxygen and Br on adjacent carbons. Okay. So we've got lots of different options, right? We can get 1,2 dibromides, we can get 1,2 diols, and then we can get the 1,2 OH-Br hybrid, all with anti-stereo selectivity. One minor point with these halohydrins is that you can use them to make epoxides. You'll think this is fun with air quotes. If you take the halohydrin and use a very, very strong base that is not a good nucleophile, you can remove the proton from the oxygen. So if we used sodium hydride, sodium hydride's not particularly a good nucleophile. It's insoluble in organic solvent, and so it just sits as a chunk at the bottom of your flask, which means it's a really, really sterically hindered base. You remove a proton to create the alkoxide, That process is not reversible because the conjugate acid of H minus is hydrogen, which is a gas and bubbles off. And then once you've got the alkoxide, you are perfectly set up for an intramolecular SN2 style reaction, backside attack of lone pairs on oxygen on the carbon bromine sigma star, and that can give you an epoxide. So that's a bit of a convoluted way to make an epoxide. There's a much more easy and direct pathway that we'll learn in chapter 12, but for now you can use the halohydrin to make an epoxide. And then lastly, with halohydrins, there is a regioselectivity issue. It's not apparent because the example molecule I've shown, in the example molecule I showed you, carbons A and B are identical. So let's come up with a situation where A and B are not identical. And let's just put a methyl group on that cyclohexene. We're going to use Br2, and in this stage, let's use, just to demonstrate that you can use things other than water, let's use an alcohol like methanol. Let's suppose methanol is our solvent instead of water. So in terms of mechanism, what we're going to see is we make a new carbon-bromine sigma bond with the pi electrons, and at the same time, lone pair electrons on the bromine attack the other carbon. We'll call them carbons A and B. And at the same time, we break the bromine-bromine sigma bond. That's going to create a bridged bromonium ion. This can happen from above the page or above the plane of the double bond. And it can also happen from below. So we would expect to get these two bromonium ions. I'm drawing them both because they're no longer identical, because A and B are not identical to each other. So these are now enantiomeric bromonium ion intermediates. Okay, so once we get there, methanol is going to outcompete Br minus as a nucleophile, and it's going to attack from the backside. So we got all of that, but we don't know which carbon it's going to attack on, carbon A or carbon B. But the regioselectivity principle here is the same as with protonated epoxides. That is, if we draw the bridged bromonium ion, the bond with the less substituted carbon is longer. Sorry, let me rephrase that. If we draw the bromonium ion, the bond with the more substituted carbon A is longer because more substituted carbon A can better tolerate a buildup of partial positive charge that happens as the Br leaves. It doesn't leave from the less substituted carbon because that carbon can't stabilize the partial positive charge as much. And that means when the nucleophile comes in, it attacks the more substituted carbon. So exactly the same regioselectivity as we saw for epoxide ring opening. The nucleophile attacks the more substituted carbon, where the buildup of partial positive charge is more stable. In the products that we get then, methanol should be on the opposite side of the molecule as the Br, and I'm drawing both enantiomers that we would get. from intercepting both of those enantiomer intermediates. And then in a second step, which I won't show you, additional methanol can remove the proton from the oxygen to give us the new ether product. Okay, so the regioselectivity here is that the methanol attacks the more substituted carbon of the bromonium ion. The stereoselectivity issue is the fact that the nucleophile and the Br end up on opposite sides of the original double bond. Yes?
Why wasn't water the one that was attacked?
Why wasn't water the one that was attacking? Because we chose to use methanol as our solvent instead of water. So there's not water here. We could have done this reaction in water, and then this would have been an OH group. So halohydrin formation works for, I should just make a note of that up at the top. It works for water and alcohols. Other questions? No? You good? Okay. So I think that takes us through 4. What happens to the H that was on carbon B? It's still there. I just stopped drawing it because I was no longer interested in it. But it's still there, hanging out, and we can draw it in. All right. So that's 4 of our 5 new reactions in chapter 10. The first was hydrohalogenation, which you don't see any syn or anti-selectivity. The second was hydration, where again you don't see any syn or anti-selectivity. The third was bromination, where you do see anti-stereoselectivity. And then the final one was halohydrin formation, where you see anti-selectivity and regioselectivity for the nucleophile on the more substituted carbon. And that's a theme for the first 2 reactions as well. With hydrohalogenation, the nucleophile ended up on the more substituted carbon. With hydration, the OH ended up on the more substituted carbon. And all of that is about the ability of more substituted carbons to better tolerate positive charges. Okay. Kyle is asking, what is the difference between halogenation and bromination? Halogenation is general. You can do these reactions with Cl2. I just chose not to do that example, so I'm sorry. Halogenation and bromination are the same thing. Hydrohalogenation is where we take the alkene and we use HBr instead of Br2, and we add H and Br across the double bond. All right, so yes?
One thing I'm trying to understand is why it attacks from the same side that the methyl group is on? Yeah. Like it pushes the methyl group up towards us?
Yes, it does.
And like, why? I guess I'm trying to.
So you can think of this reaction as SN2 backside attack with inversion of stereochemistry, with inversion of configuration. So this may be easiest to draw if we were looking at a bromonium ion like this, and I guess I'll make it chiral just because. So if we had water or methanol attack from the backside, Br leaves, so the new stereochemistry is going to have the methoxy group here. Now on that carbon A or whatever that was attacked by methanol, the methyl group will still be pointing out towards us but angled towards the top of the page and the ethyl group will still be pointing towards, the ethyl group will be pointing into the page away from us, but still sort of pointing up towards the top. If we were to look at this reaction from a slightly different view, we might have drawn the same bromonium ion this way, and we might have drawn methanol attacking that bromonium ion. Br would be here. Because methanol attacks from the backside, it pushes that ethyl group upward and then ends up there. These two are the same thing. These two are the same thing. So it's just, I think the confusion is, we're a little bit unfamiliar with drawing SN2 reactions in the context of a three-membered ring, but you're just getting inversion of configuration with backside attack. Is that a little clearer? Okay, yeah.
I thought with SN2 configuration, because it's substituted so much on that carbon A, that it would want to go to carbon B that's less substituted.
Right. Yes. I mean, normally that would be the case, but that's what we were, last time when we talked about epoxides, we talked about how the protonated epoxide starts to leave. Let's see, did we get that far? Yeah, when the epoxide is protonated, the OH group starts to leave. It leaves from the more substituted carbon because that can build up a positive charge, but you never get to a fully planar carbocation intermediate. The OH group on top is still blocking the top face of this molecule, so the nucleophile Br minus comes in from behind. This is an example of an SN1-like SN2 reaction. The leaving group has done a lot more leaving at this stage than the nucleophile has done coming in. That means there's going to be a buildup of positive charge. It happens on the more substituted carbon where it's more stable, and that governs which of the two carbons gets attacked. It's exactly the same thing going on here. It's SN2, we'll call it an SN1-like SN2 reaction in the sense that you get regioselectivity for the more substituted carbon, but it's SN2-like because you get backside attack. So this occupies sort of a space in the messy middle between SN1 and SN2.
So does that change depending on what the solvent is?
Will that change depending on what the solvent is? I think it could, but not in any way that I am prepared to predict. All right, good. What else? All right, so the last reaction we'll introduce in chapter 10 is a reaction that's cool because it does two things we haven't been able to do yet. First, it's regioselective. It's a hydration reaction. It's an overall hydration reaction that is adding water across a double bond that is regioselective for OH ending up on the less substituted carbon. And it's stereoselective for syn products. So this is sort of the backwards version of what we've done so far. The name of the reaction, I guess we could call it's formally a hydration reaction, but that's not, but the mechanism is different. The reaction is called hydroboration / oxidation. And it doesn't necessarily fit that great here because we're not going to talk about the oxidation mechanism, but it's a useful and interesting counterpoint towards generating hydration products from alkenes. All right, so to demonstrate this, suppose that I used this starting material and I wanted to do alkene hydration, so I use catalytic H2SO4 and I use, sorry, can't write, catalytic, and I use water. That's going to generate a carbocationic intermediate, which is going to be attacked by water at the more substituted carbon. In the first step, I would pick up a proton from my acid. Okay? And so I get the OH on the more substituted carbon, and we call that Markovnikov regioselectivity. You don't have to call it Markovnikov, but your book will. Now, supposing I wanted to take the same starting material, but I wanted the OH on the less substituted carbon. Do we have a way of doing that? And the answer is yes, and it's this hydroboration oxidation reaction. So our solution here is to use borane, BH3. Boron is a second row atom just in front of carbon on the periodic table. It's when neutral, bonded to only 3 things. It's an electrophile because it has an empty p orbital. So you use borane for the first step, and then the second step you have to use hydrogen peroxide under basic conditions. These may be reagents that you need to memorize. The first step is called the hydroboration step, and the second step is called the oxidation step. So I will only show you the mechanism for the hydroboration step, and to do this I'm going to draw the alkene from a side-on perspective. And the reaction is going to be nucleophile attacks electrophile. Our alkene is our nucleophile. And then our boron molecule, borane, is our electrophile. And the relevant orbital on the nucleophile is the HOMO, which is the carbon-carbon pi bond. The relevant orbital on the electrophile is the LUMO, which is the empty 2p orbital on boron, which, you know, we could draw. We know what a 2p orbital looks like. Borane is planar, trigonal planar, sp2 hybridized, and here's the empty p orbital on boron. Another useful thing to know about boron is that its electronegativity is actually less than that of hydrogen. So you'd expect a little bit of delta minus on the hydrogen and a little bit of delta plus on the boron. And that's important for determining the regioselectivity of this reaction. All right, so first step is pi electrons attack boron. All right? And as that process happens, imagine what happens to boron when it's attached to 4 things, right? If boron's attached to 4 things, it has a formal negative charge on the boron, right? But we know that boron is less electronegative than hydrogen, so probably a lot of that formal negative charge is actually out on the hydrogens. What this means is, as this bond starts to form, the already partially negative hydrogen gets even more negative. And as it does, it leaves with its electrons and attacks the more substituted carbon. The product that you would get from this is one in which the boron and the hydrogen have added to the same face of the original alkene. Now, you could ask, why does the proton end up on the more substituted carbon? The reason for this has to do with the transition state for the hydroboration reaction. So let's again view our alkene from the side. And in the transition state, the pi bond is breaking and a new sigma bond is being made between boron and carbon. And we're going to choose to make that new sigma bond between boron and carbon such that partial positive charge builds up where it's more stable. In other words, if this is carbon A and this is carbon B, we're going to selectively choose to start making the new carbon-boron bond with B so that we're stealing electron density away from the carbon that can best tolerate it. So really, this is exactly the same thing as we saw with alkene hydration. If you remember, in alkene hydration, the first step was proton gets removed and we get an intermediate where the positive charge is on the more substituted carbon. The only difference here is that instead of proton being attacked, we're attacking the boron. All right? So that's going to cause a buildup of partial positive charge on the more substituted carbon where it's more stable. At the same time as that bond is forming, the hydrogen boron bond is getting longer. There's a buildup of partial negative on this hydrogen, and we choose to make a new bond with hydrogen and carbon, the carbon that has the partial positive charge on it. Now, another explanation which may be simpler and which you could use as well is sterics. The boron is bigger than a hydrogen, and therefore we put the boron on the less substituted carbon. That explanation works okay too. All right. So the product of this reaction is called, of step one, is called an alkyl borane. And you can use these types of intermediates for lots of different things, but if you subject them to peroxide under basic conditions, what you end up doing is replacing the BH2 with an OH group. And you do it without changing any stereochemistry. There isn't any here to talk about, but and the reason you don't change stereochemistry has to do with the mechanism of that reaction. If you're interested in it, I can show it to you outside of class. It's not that hard, but it's also sort of a distraction and not that important for what we want to do. Okay, so what we've just demonstrated is that hydroboration and oxidation are regioselective for putting the OH on the less substituted carbon. We need maybe one other example to demonstrate the fact that this is indeed a syn addition. So we'll use our favorite methyl cyclohexene. If we do hydroboration oxidation, we'll first make an alkyl borane in which the hydrogen and the BH2 get delivered to the same side as the original alkene. And if the molecule or intermediate we make is chiral, we have to make both enantiomers. And then in the second step where we add peroxide and hydroxide, we can replace the BH2 with hydroxide without changing the stereochemical configuration where the boron used to be. So this demonstrates the fact that we get syn addition of hydrogen and OH across the double bond, but we get the OH on the more substituted carbon. And this is exactly backwards from what we would get if we tried the same reaction under just strongly acidic conditions. We would end up with the OH group on the more substituted carbon, and there wouldn't be any stereochemical issues to speak of. Yeah?
Just a quick question, is that alcohol on the product coming from the hydrogen peroxide or from the
Is the alcohol in the product coming from hydrogen peroxide? Yes. Yeah. And it's, like I said, it's not that big of a deal, but it's complicated enough. I used to teach it in 351, and then I regretted it because it was difficult to get through and had a lot of steps, but it also didn't really add a lot conceptually. So if you want to see it, you can look it up. It's on Wikipedia or on the internet, and it's fine. It's not that bad, but it's sort of extraneous. Other questions? All right. So that's a little bit faster through chapter 10 than I thought we would be. What I want to do next time, before we move on completely from chapter 10, is to show you how the principles that we've learned so far can help you see how we would get from a starting material that looks like this to a much more complicated product that looks like this. This molecule is geranyl pyrophosphate, which I think I showed you before. This molecule is limonene, and the way you get from here to here involves carbocations being attacked by alkenes, and involves a lot of regioselectivity issues that you're already prepared to deal with based on what you've learned in chapter 10. So I think we'll take the next lecture to talk about this kind of chemistry. It's called terpene chemistry. It's not in your book, but it will be in your notes, and it's kind of fun. So, fun to me, anyway. We'll see you next time.